Could you please explain what is cosmic microwave background radiation? Good question. CMBR. So the cosmic, okay, so let's say I have a telescope. Okay. I take the telescope, I look out into the interstellar space, and I see darkness, and I see some stars and some galaxies, but it's mostly black. It's mostly dark, right? Now you can take the most powerful telescope that you have, the most powerful optical telescope that you have, and you will again see, you will be able to see many more stars and galaxies. You will be able to see much further away, but you will see this darkness. And yet, when you have a very powerful and sensitive radio telescope, for example, then you detect that a certain kind of noise in the background. It's as if there is a certain glow, a very weak glow that permeates the entire universe, but it's not visible to the naked eye. And the wavelength of this glow, the wavelength of this radiation, it is electromagnetic radiation. Its wavelength is about from a millimeter to a meter long, and it's extremely cold. It's about 2.7 or so degrees Kelvin above absolute zero. So it's almost at absolute zero, just a little fraction, just a little notch above the absolute coldest temperature that you can have in the universe. But it is still there, and this radiation, this ancient glow, permeates the entire known universe. And what this is it is the oldest electromagnetic radiation that was ever uh, formed in the universe. It dates back to about 370,000 years after the Big Bang, during the epoch of recombination, when when protons and electrons first combined to form stable atoms, to form stable hydrogen atoms. So this is the epoch of recombination, and that's when this radiation first was first formed. And this radiation persists to this day. It was much hotter earlier during that epoch of recombination. Today it has become very cold, and its wavelength has shifted. It's become very much longer. So it's in the microwave wavelength, and it is the oldest radiation that we know. It is almost like the afterglow of the Big Bang itself, almost like that. So it tells us a lot about the early universe. It is one of the major proofs that we have of the Big Bang theory, the Big Bang model of cosmology. So there are two things that essentially have helped us understand that something called the Big Bang actually happened. The first thing is that there is this accelerating expansion of the universe, the cosmic redshift that we see. And the second is the detection of this cosmic microwave background radiation. So it was first detected in the 1960s by accident, purely by accident, purely by chance. And those lucky guys who discovered it got the Nobel Prize for just stumbling into it. Then in the late 1980s, the first proper survey of this radiation was done. A satellite called Background Explorer was sent up, and it mapped the distribution of this radiation. It found that it is not completely uniform. There are anisotropies and other such patterns. So it is an outcome of primordial quantum fluctuations in the very early universe, which created regions of less density and more density and over densities, etc. So we can see that pattern in the distribution of cosmic microwave background radiation today. So in the 1980s, you had the COBE satellite. Then in the early 2000s, you had a WMAP experiment, a new satellite that was pent up. It gave us a better understanding of CMBR. And then recently, about a decade ago or so, you had the Planck satellite, the Planck experiment, which gave us an even better understanding of this ancient radiation. So that is what cosmic microwave background radiation is. It's a very interesting phenomenon. It essentially proves that the Big Bang actually happened.